All right, so what we're going to do in Chapter 8 is apply what we just learned in Chapter 7 to the periodic table. Okay, so we know from Chapter 7 that as energy levels increases, as n goes from 1 to 2 to 3 to 4, the energy level also increases. And it's also true that within the same shell, a P is a higher energy than a S, and a D is higher than a P, and so forth. So if we only have one electron, then it's pretty easy to see what's happening. But what do we do if there's more than one electron? How do they populate these orbitals? So that's the main goal of this chapter. Okay, so we saw in Chapter 7 that electron pairs that are in the same orbital have to have opposite spins. And they had like a m sub s equal plus 1/2 or minus 1/2. It's because electrons behave as if they were tiny spheres spinning on their own axis. We'll see a picture of that in just a second. And so, in fact, if you take a beam of hydrogen atoms and send it through a magnetic field, half of them will be attracted to the positive pole, and half of them will be attracted to the negative pole. Again, this is because the electrons are spinning. So a spinning electrical particle acts like a magnet. Half of them are spinning clockwise and half of them are spinning counterclockwise, and they correspond to the plus 1/2 and the minus 1/2. And you can see there are two different pictures, but one goes with the spins with the magnetic field, and the other is against the magnetic field. Okay, so what we're going to do, those were just some things to keep in mind. We're going to come up with what's called an electron configuration. It's a way of showing where the electrons are distributed in the atom. Okay, the notation will list things like subshells, shells, subshells, and then a superscript indicating how many electrons are in that subshell. For example, lithium has 2 electrons in the 1s subshell and 1 electron in the 2s subshell, so its electron configuration is 1s2, 2s1. We're going to sort of start from the beginning and derive these. Okay, an orbital diagram actually is a little bit more than the electron configuration, and it shows the actually shows the electrons in the subshells. So for an electron configuration, each orbital is represented by either a line or a circle or a box. It sort of depends on what you're using. In this presentation, we're going to show them with a circle. And we're going to label each orbital and each subshell. So we know that on the first shell there's only a 1s subshell, and we know that the 1s subshell has 1 orbital, so that's represented by 1 circle. The 2s, the second shell has 2 subshells, the 2s and the 2p, and the 2s has just 1 orbital, but the 2p has 3 orbitals, so we represent those circles there. And then what we're going to do is put arrows in to represent the electrons. And notice that if we do the up arrow, it represents the positive 1/2, and if we do a down arrow, it represents the negative 1/2. So let's start with some guidelines. First is the Pauli's exclusion principle, and we've actually already talked about this in a different way, but the Pauli's exclusion principle says that no 2 electrons can have the same 4 quantum numbers. Now, if we're talking when we drill down to the subshell or the orbital level, that means N and L and M sub L are all fixed. So if we're talking about the 2p subshell, then N is 2, L is 1, and the M sub L, whether we're in the first box, the second box, or the third box, or the circle, are all fixed. And so to put one to get the 4th quantum number, which is plus 1/2 or minus 1/2, that is that indicates that the 2 electrons have they have the first three numbers are the same, the fourth number is different. And since you can't have more than 2 electrons in any orbital, you can never have more than, no electron can have the same 4 quantum numbers. Okay, so just a little bit of review from Chapter 7. The maximum number of electrons are shown here. So for an S subshell, since there's only one orbital, we can only have 2 electrons. A P subshell has 3 orbitals and a total of 6 electrons. A D subshell has 5 orbitals and 10 electrons. And an F subshell has 7 orbitals and 14 electrons. All right, now the next thing that we're going to talk about is the Aufbau principle. So we want to, basically, we know from the hydrogen atom, electrons can jump around wherever they want to be. As long as they're on those energy levels, they can jump from one level to the next. If we were to do that with many electrons, we would have an infinite number of configurations because they could actually exist anywhere. So what we're going to do is actually only draw electron configurations and orbital diagrams for an element in its lowest energy. So the electrons are in the lowest energy they possibly can be. This configuration is called the ground state configuration because it's the lowest energy level. And then any other configuration would be an excited state. So your table lists a number of electron configurations, orbital diagrams, and you can find them in your book. But let's talk about how they're how we get to them. So if we wanted lowest energy and there were no restrictions, then all the electrons would be crowded down in the 1s orbital. But according to Pauli's exclusion principle, we know there can't be more than 2 electrons in any orbital. So orbitals fill in increasing order. So once the first 2 are in the first shell, the next electrons go in the next higher shell and the next higher shell. And remember that you can't have more than 2 electrons per orbital. So this is called the Aufbau principle or the building up principle. So this is the actual order for the filling. 1s, it starts out all right, 1s, 2s, 2p, and then 3s, 3p. But then we run into a little glitch. And notice that the 4s is before the 3d, and then the 4p, 5s, then the 4d comes before the 5p, and etc. You can remember this order by writing it down, or there's a mnemonic in a minute that you'll see, or by the end of this chapter you should be able to look at a periodic table and remember this order. So this picture gives you a little bit or better idea of why the order is the way it is. So in general, the second shell is higher than the first shell, and the third shell is higher than the second shell, and the fourth is higher than the third, and etc. And also within a shell, P's are higher than S's, and D's are higher than P's, and F's are higher than D's, etc. But when you notice that at the top of the energy, they start to get closer and closer, and so they start to overlap. So if you follow along, you'll notice that we go, well, 1s, 2s, 2p, 3s, 3p, but then the 4s is slightly lower energy than the 3d. So the 4s fills, and then the 3d, and then the 4p. Then the 5s is a little bit lower than the 4d, and the 5p is lower than the 4f, well, actually 5p, then 6s, then 4f. So you start to see the order. Again, by the end of this chapter, you'll be able to see how you can remember this order without looking at this chart. And here's a little mnemonic device. That's one way that you can remember it if you want to write down the order and see how those arrows kind of follow the trend. You can remember it that way. So the building up order does correspond to increasing energy. So if we fill the orbitals of the lowest energy first, then we get the lowest total energy, or what we call the ground state electron configuration. Then what we're going to do is use a shorthand notation to make the electron configuration, and we'll see how to do that in a minute. So just keep in mind that the number of electrons in the neutral atom will always equal the number of protons because it's neutral, and so it's the same as the atomic number. All right, so here are some examples. Lithium only has 3 electrons, and so the first 2 can go in the 1s orbital, and then the next one has to go to the next highest orbital, which is the 2s orbital, and we put 1 electron in there. And just note that it doesn't matter, the first electron, it doesn't matter if it's up or down. You just have to make sure when there's 2 of them that they are opposite. Okay, beryllium has 4 electrons, so the first 2 go in the first orbital, and the second 2 will complete the second orbital. Boron, which has 5 electrons, since the 1s and 2s are both filled with 2 electrons, the next electron has to go in the 2p orbital. Now, when we get to carbon, we get a little bit of an issue and we're not sure what to do. So we've got 2 electrons in the 2p. All right, so there's actually a couple of different options that we could do with our electrons in carbon. So you can see diagram 1 has them, as we just saw them, with 1 each in 2 different orbitals, both with the same spin. Diagram 2 shows 2 different electrons in 2 different orbitals with opposite spin, and diagram 3 shows the 2 electrons in the same orbital. Well, it turns out that diagram 1 is the most correct. And this is because each of these actually have slightly different energies associated with them. And the lowest energy is diagram 1. Diagram 3 is probably the highest energy. So let's talk about that a minute. What we're using is called Hund's rule, and it says that the lowest energy arrangement, or the ground state of the electrons, is gotten by putting electrons into separate orbitals within the same subshell with the same spin before pairing them. So this gives you the lowest energy possible. So looking at carbon again, the best option is this one. So again, when you have more than one orbital in the same subshell, first of all, you need to put all of the we need to represent all of the orbitals, even if there's no electrons in there. So whenever you write the 2p subshell, you should put 3 circles or 3 lines or 3 boxes or whatever it is that you want to use to represent the orbitals. And then the electrons will start filling them, and then you fill them up. 1 in the first one, 1 in the second one, 1 in the third one, and they should all match spins, and then you can go back and fill them up the rest of the way. So as you can see here, this is nitrogen, so 1 more electron, 2p3, has 1 in each orbital. And then for oxygen, the next electron, instead of going up to the next highest energy level, it would definitely want to fill up this subshell first. So now it will go ahead and pair up to the first orbital, and then if you keep going, you'll fill up. I think that's on the next slide. And then you can see for fluorine, you end up putting 2 in each of the first 2 and 1 in the last one, and then finally neon fills up that subshell. So yeah, this is just what I was saying. Nitrogen has 3 each up, then oxygen pairs up 1, fluorine pairs up the next one, neon fills up that subshell. Note that sometimes you notice in the one page I use circles as orbitals. In this case, you could represent a line as an orbital, or you can use a box as an orbital. It doesn't really matter. Whatever you like the best. Okay, so once the second shell is complete, we start putting electrons in the third shell. So after neon comes sodium. Sodium has 1 electron in the third shell, so it's in the 3s1. Magnesium has 2, so it fills up the s orbital, so 3s2, the s subshell. Aluminum then has 3 electrons in the third shell, so it has 3s2, 3p1. And here you can see all the different orbitals up to krypton. If you look at it closely, you might find a few little glitches, which we'll talk about in a little while. What some of you may have started to notice is that different subshells have different parts of the periodic table. So in fact, the first two rows will be those elements filling up the s electrons of whatever shell you're on, 2s, 3s, 4s. The p electrons are over on the right hand side, so, and remember there's 6 p electrons total, and so there's 6 columns, the blue on the right hand side. 2p, 1, 2, 3, 4, 5, 6. The d electrons, there are 10 of them, and they take up the transition metal area, so where the kind of orangish, those are the d subshells, and there's 10 electrons in any d subshell, and so 10 boxes. And then finally the f subshell come after. They actually, as you can see, go between the 6s, the 4f goes between the 6s and the 5d, and then the 5f goes between the 7s and the 6t. And so actually, if you can remember where everything is on the periodic table, you can just remember the filling order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, etc. And then 6s, 4f, 5d, 6p, 7s, 5f, 6d, etc. All right, so if you look at the configurations of the noble gases, what you'll notice is that they all fill up the highest energy level S and P subshells. All right, so helium ends with 1s2, and that's its highest energy level. Neon fills up 2s2, 2p6. Argon, 3s2, 3p6. Never mind the Ds, but the Ps and the S's are filled up. And then krypton fills up its highest energy level, the 4s2 and the 4p6. And so what we can do is actually shorten all the configurations by using these noble gases in brackets to represent that level. So, you can say, well, everything's in that element up to this noble gas, and then here's what's extra. So sodium, you can see, instead of writing 1s2, 2s2, 2p6, 3s2, we can say, well, it has everything neon has, and then it also has a 3s1. Chlorine has also everything neon has, but it also has a 3s2, 3p5. Manganese has everything, so you go up to the noble gas just before it, which is argon. That ends with 3p6, so in addition, manganese has 4s2, 3d5. Barium, as you can see, goes all the way up to xenon plus a 6s2. So if we look at the periodic table, I can show you a little bit how to write noble gas configurations the easy way. It's to look at the periodic table, find the element that you're looking at. So for example, if we want to write the electron configuration, the noble gas configuration for sulfur, find where sulfur is. Go back to the noble gas in the row above it, so this would be neon. Write that in brackets. Then you want to list everything that comes between neon and sulfur. So we have 3s2 and then 3p4. Make sure and include the one that you're looking for. Sulfur would be the fourth one. Okay, in the same way, for technetium, again, technetium right there, we would go back to the last noble gas, which is krypton, and then write everything that comes between krypton and technetium. So krypton in brackets, and then 5s2, and then 4d5. So that's how you write a noble gas configuration. Then what you can see is when we use this notation, so here you can see that they all end up with the same configuration at the end, and this is this is what explains why elements in the same column have similar properties. It's because they have a similar electron configuration. These are in their highest energy level. So you can see here beryllium ends with 2s2, magnesium ends with 3s2, calcium with 4s2, strontium with 5s2, and barium with 6s2. So these are all in group 2A, and notice that they all end with s2 in whatever level they're in. Okay, the electrons that are in the outermost shell of an atom are called valence electrons. So we have the noble gas core, and then we have the valence electrons. And it turns out that all these valence electrons are the ones primarily involved in chemical reactions. So that's really the only ones we're worried about. elements within the same group have the same valence shell configuration, just like we saw. So everything in group 2A all ends with S2. And like I said, this accounts for the similarity of chemical properties within one same group. So I already showed you this a little bit, but again, looking at the periodic table one more time, this is how we can remember the Aufbau sequence. Remember that you really only need the configuration of the outer electrons, and we can determine this from their position on the periodic table. And then the total number of valence electrons equal its group number if you use the A group series. So group 1A has 1 valence, group 2A has 2, group 3A has 3, 4A has 4, 5A has 5, 6A has 6, 7A has 7, and 8A has 8 valence electrons. Okay, so again, this is just the same that I showed you before. So you can remember the order: 1s, 2s, 2p, 3s, 3p, 4s, etc. All right, so earlier we saw that there might be a few exceptions to the build-up principle, and this happens because actually there are some other arrangements that are sometimes a little bit lower energy than the normal expected. So for example, chromium, which has 4s2 3d4, that's what we would expect to write. Actually, because it's a little bit more stable to have a half-fold 4s orbital and a subshell and a half-filled 3d subshell. So 4s1 3d5 is actually slightly lower energy than 4s2 3d4. Although that's because 4s and 3d are so close in energy that there's some extra savings in that half-filled subshell. And then similarly with copper, to be almost filled 3D subshell is a little higher energy than having a full 3D subshell and having a half-filled 4s subshell. So the 4s1 3d10 is slightly lower energy. Either one of these would be fine. If I asked you for the configuration and you gave it to me, I would count either one of these. So I just wanted to explain to you what's happening.